Imagine you're training a language model to answer questions. You give it a prompt like, explain quantum entanglement in simple terms. Now here's the twist, there isn't just one correct answer. You could explain it using analogies with spinning coins, or entangled dice, or even a pair of magical socks. All are valid, just different ways of saying the same thing. This is the heart of a growing frontier in machine learning, learning from multiple correct answers. In traditional supervised learning, we assume each input maps to a single, unique label. But in real-world tasks, like open-ended question answering, dialogue systems, or recommendation engines, correctness is often set-valued. A prompt may have many acceptable completions, all equally valid. So how do we build learning algorithms that respect this flexibility? And how does the type of feedback we give the learner change everything? Today, we dive deep into a groundbreaking paper by Alir Zapor, Farnam Mansouri, and Shai Ben David, unifying 3 feedback models in online learning with multiple correct answers, and revealing a trichotomy of regret bounds that reshapes our understanding of learnability. Let's break it down. The setup, a game of guessing the right answer. We're in an online learning setting. Over T rounds, an adversary presents an input XT, along with a set of acceptable labels SDY, and our learner must output a single label TY. The learner suffers a loss if T SD. The goal? Minimize cumulative loss across all rounds. But here, S the key. The feedback the learner receives varies dramatically depending on the model. There are 3 distinct feedback regimes. Mistake unknown feedback. The adversary reveals only one correct label YT-SD, but no information about whether the learner's prediction was correct. Mistake known feedback. In addition to YT, the learner learns a binary signal, whether their prediction was correct. 1. Set valued feedback. The learner sees the entire set SD. Full information. These models reflect real-world scenarios. Mistake unknown. Think of LLM training data, a prompt paired with a single human-written response. Mistake known. During interaction, the user says, that's not quite right. Feedback on the specific output. Set valued. A gold standard dataset where every acceptable response is listed, useful for theoretical analysis. Combinatorial dimensions, the geometry of learnability. To understand when learning is possible, we turn to combinatorial dimensions, a powerful tool in online learning theory, inspired by Littlestone's work on binary classification. These dimensions are defined via trees. Imagine a tree where each node corresponds to a possible input and label choice. A tree is shattered if for every path from root to leaf, there exists a hypothesis that is consistent with the path and makes a mistake at each step. We define 3 dimensions, one for each feedback model. LD unknown, mistake unknown Littlestone dimension. Captures how many mistakes a learner must make in the worst case under limited feedback. LD known, mistake known Littlestone dimension. Accounts for the extra information, whether a prediction was correct. LD set valued Littlestone dimension. Matches the set Littlestone dimension from prior work, measures how complex a class is when full label sets are revealed. Crucially, we have the hierarchy. LD set less or equal to LD known, less or equal to LD unknown. And here's a profound insight. All 3 collapse to 0 if, and only if every input has at least one common label across all hypotheses. That is, the intersection of all possible label sets is non-empty. If no label is universally acceptable, no learner can succeed in the realizable case. Realizable learning, the perfect world. In the realizable setting, where a perfect hypothesis H exists that always outputs the correct set SD, we can characterize the optimal mistake bound for any class. Theorem, for any hypothesis class H, the minimum number of mistakes any algorithm can make in T rounds is min LD unknown H, T for mistake unknown, min LD known H, T for mistake known, and min LD set H, T for set valued. This is tight. There exist algorithms, standard optimal algorithms, that achieve these bounds. The key idea: maintain a set of candidate hypotheses, prune them based on feedback, and use a greedy selection rule, like minimizing the worst-case remaining mistake budget. These results generalize prior work by Joshi et al. 2025 and Raman et al. 2024, but now applied to infinite hypothesis classes, not just finite ones. A shocking discovery, the trichotomy of regret. Now the real drama begins in the agnostic setting, where no perfect hypothesis exists. The learner must compete with the best possible hypothesis in the class, but the adversary can choose any sequence of label sets. And here, S where the 3 feedback models diverge in a trichotomy of regret. Mistake unknown. Regret can grow linearly in T, even for a tiny class of just 3 hypotheses. Why? Because the learner gets almost no information. It sees only one correct label per round, and no feedback on its own prediction. So no meaningful regret bound exists in general. This is a fundamental limitation. Mistake known, regret is sublinear bounded by O square root YTLD known H log T. The extra Y factor comes from the lack of full information. Only the expert who recommended the chosen label knows whether they were wrong. This is where tools from Bandit Learning come in. The authors reduce the problem to prediction with expert advice under partial feedback, using a variant of EXP4. Set valued, regret is constant for many classes, and in general bounded by O square root TLD set H log T. No dependence on Y. Why? Full feedback means the learner can precisely update every hypothesis and use a weighted majority algorithm that keeps total weight non-increasing. This trichotomy is profound. Mistake unknown, impossible to get good regret. Mistake known, sublinear but with a penalty for label set size. Set valued, constant regret for many classes and always sublinear. An example that proves it all. Let's take a simple class. Domain x equals x, 1 input. Label set y, 123. Hypotheses. h1 x equals 23. hx equals 13. h3 x equals 12. This class has LD unknown LD set equals 1, so realizable mistake bounds are small. But now, in the agnostic setting. Mistake unknown. Any algorithm must have regret greater or equal to T2 in expectation. Why? The adversary picks YT uniformly at random. The learner's prediction is based only on past YT, not ST. So the adversary can always pick ST to maximize error. Set valued, use the weighted majority algorithm. Assign weights to hypotheses, update them based on whether they were correct. The total weight never increases. And the regret is bounded by log 2, 3, constant. This example shows the power of full feedback. Even in an adversarial setting, constant regret is possible. From online to batch, sample complexity. The authors also show how online results imply batch learning guarantees via standard online-to-batch conversion. For realizable learning. Mistake unknown, sample complexity O tilde LD unknown H slash epsilon. Set valued, sample complexity O tilde LD set H slash epsilon. For agnostic learning, they prove. If a class satisfies 2H, X backslash H, X less or equal to H, X for all H, H, and X, then it is agnostic set valued learnable with constant regret in the online setting, and thus sample complexity O log H slash epsilon. This resolves an open question from Joshi et al. 2025, and shows that richer feedback enables stronger generalization. Why this matters? This work isn't just theoretical. It has real implications. For LLM training, we now understand the cost of using only one example per prompt. Mistake unknown feedback is inherently weak. Regret can't be bounded. For evaluation, set valued feedback, while expensive, gives the strongest guarantees. It's ideal for benchmarking. For algorithm design, the trichotomy tells us feedback quality is not just a convenience, it's a fundamental bottleneck. And the takeaway? You can't learn from multiple correct answers without the right feedback. The type of supervision you give shapes whether learning is possible at all. Final thoughts. This paper unifies 3 feedback models under a single framework. It provides complete characterizations of realizable learnability, a sharp trichotomy in agnostic regret, tight sample complexity bounds, and deep insight into the role of feedback in multi-label learning. It's a landmark in online learning theory, bridging the gap between theory and practice in a world where correctness is never a single point, but a set. So the next time you train a model to answer a question, ask yourself, what kind of feedback am I giving? Because the answer might determine whether learning is even possible. Thanks for watching. If you found this deep dive valuable, hit like, subscribe, and let me know in the comments. Which feedback model do you think is most realistic for real-world AI systems? Until next time, keep learning, keep questioning, and keep pushing the edge.